This is the very beginning of us. 4.6 billion years ago, on an indistinct arm of the Milky Way galaxy, a solar system, our solar system, was born. It took eons for the massive clouds of dust and gas known as the protoplanetary disk to coalesce into the known planets. In those early days, the solar system was a violent place, where mountain-sized and even planet-sized piles of rock and ice would often come together in massive, tumultuous confrontations. Some collisions were so powerful that the energy they released would dwarf the simultaneous detonation of every single weapon ever made in the history of man. Merging of such celestial leviathans could literally break a world in two. Such cosmic collisions have often sent their rocky remnants wandering throughout the solar system.
If you've ever seen a meteor streak across the sky, then you may very well have seen part of the asteroid Vesta. And these bodies contain a lot of clues as to what was going on right at the very beginning. This mission not only explores in space and tries to find the new frontiers in space, but also is interested in going back in time and trying to understand where the solar system came from.
And to accomplish this, a spaceship, the first spaceship capable of traveling between and loitering over two distinct worlds, is required. One whose engine will work without fail for years at a time. One capable of propelling itself faster and further than any other spacecraft has pushed itself before.
Now we're really going to be investigating a previously unknown part of the solar system. A lot of people think of asteroids as little chips of rock, but Vesta and Ceres are big places, and I think they hold a lot of really cool secrets.
One of our major tasks is to explore the earliest epoch. We want to know what the solar system was like at the very beginning.
In 2001, NASA chose to implement Dawn as a Discovery Program mission. Getting a mission from paper to launch pad to the darkest regions of the asteroid belt is no easy task.
To accomplish a project like Dawn, it really takes a team. So it takes a lot of expertise from JPL as well as institutions literally around the world.
Here at Orbital Sciences Corporation, we are building the Dawn spacecraft.
UCLA provides the science side of Dawn, so we're doing the science planning.
Here at Los Alamos National Laboratory, it's my job to get this scientific instrument designed, built, launched, and to get the data returned.
I'm working at the Institute of Physics of the Interplanetary Space in Rome. We have provided the Dawn mission for a visual infrared imaging spectrometer.
I work at the Max Planck Institute for Solar System Research in Germany, and the camera has been built by our institute.
JPL is responsible for the overall implementation of the Dawn project. We're responsible for designing the system, for designing the mission, navigating it, operating it, and bringing all the pieces together.
We have our team. It's a great team. Now we need to do our homework and execute and have a lot of meetings.
Dawn team members have meetings about mission science, computer hardware, computer software, spacecraft design, navigation, and meetings on how they will all work together. And each and every one is filled with its very own language, the idioms of deep space exploration. When the Asteroid Belt Explorer deploys its two 27-foot-long solar arrays, the spacecraft will extend almost 65 feet. These massive solar panels provide Dawn over 10 kilowatts of electricity, providing the electrons to run the vehicle's computers, science instruments, and its out-of-this-world propulsion system. More electrical excellence than mechanical marvel, Dawn's remarkable ion engines employ electrical currents, magnetic fields, and xenon, a gas more than 4 times heavier than air. When maneuvering is called for, the high-tech innards of an ion engine change the xenon into a positively charged plasma and accelerates it out the engine at speeds over 78,000 miles per hour, 21 miles per second.
The thrust from the ion engine is very gentle. In fact, The ion engine pushes on the spacecraft as hard as this single piece of paper pushes on my hand. And so with the air resistance and gravity here on Earth, the ion propulsion system wouldn't work.
Dawn's ion engines can run for literally months or even years at a time.
It would take Dawn about 4 days to go from 0 to 60 miles per hour. But instead of thrusting for 4 days, if we thrust for 40 or 400 or 4,000 days, the spacecraft can achieve very, very high speed. And in fact, Dawn will achieve a much, much higher speed than any spacecraft has ever achieved with its propulsion system.
Dawn's journey into the heart of the asteroid belt will require 4 years and 1 Mars flyby. A voyage to discoveries that is sure to encounter its share of solar storms, interstellar particles, and the unknown of deep space.
It's so cool going to the asteroid belt. It's this ring of broken up debris between Mars and Jupiter, but we've never had the capability to go there, stop at an asteroid, and explore it.
The asteroid belt is really fascinating because it's kind of like the boneyard of material that's left over from forming all these planets. There are these extremely interesting protoplanets like Vesta and Ceres.
Named for the Roman goddess of the hearth, Vesta is the brightest asteroid in the solar system and the only one visible to the naked eye.
Asteroid Vesta is a remarkable place. In one sense, it's sort of like our moon, but in another sense, it's sort of like the Earth. It's got a iron core, just like the Earth does, and it may have had many of the processes acting that the Earth has acting today.
In October of 2011, after a journey of 1.9 billion miles, the Dawn team will commence science operations at asteroid Vesta.
The 3 science instruments on Dawn all work together in a very complementary fashion to tell us about the surfaces of the body. So the visible and infrared spectrometer in combination with the gamma ray neutron spectrometer are giving us this detailed information on the composition.
GRAND measures gamma rays and neutrons that escape from the surfaces of Ceres and Vesta, and the gamma rays provide you with a characteristic fingerprint that you can use to figure out what the surface is made out of from the standpoint of what elements are there.
The framing cameras are giving us the overall context of what the surface looks like, and from that we're mapping out geologic provinces. These are giving us the really detailed look at what's on the surface, and from that we try to work back to how the whole thing was put together and what happened to it. The gravity science then gives us the third dimension where we can peer into the body and see how the interior has evolved over time.
We can start to put together, along with the information from the other instruments, a complete picture of how the planet evolved.
Dawn's mission doesn't end with asteroid Vesta. We're going to spend more than half a year there collecting a fantastic amount of science data, but then when it's over, Dawn is going to leave orbit from Vesta, travel around to a different part of the asteroid belt, and visit, in fact, the largest asteroid, asteroid Ceres.
The 1 billion mile transit between Vesta and its second science target will make Dawn history's first true interplanetary spaceship. In February 2015, Dawn will arrive at the dwarf planet Ceres.
A dwarf planet is a body that did not really evolve into a full-size planet.
Scientists believe Ceres represents a transition from the rocky terrestrial planets of the inner solar system and gaseous and icy worlds of the outer solar system.
It's an extremely interesting body for us to study. It's a frustrated planet in the sense that it would have continued to accrete into a large body had Jupiter not moved into the neighborhood and started to sweep up all the material. So what we have is a little a capsule of information about what the conditions were in the initial dust cloud of the primordial solar system.
Scientists believe Ceres may contain, below its surface, enormous amounts of water, perhaps even more fresh water than in all the freshwater lakes on Earth.
In the League of Planets, Ceres may be considered a dwarf, but for what it can tell us about the science of the solar system, Ceres is a giant.
To me, what's most important about Dawn is the information we're going to get back from Vesta and Ceres. From my point of view, these are among the last unexplored worlds in the inner solar system.
NASA's Dawn mission is not only a look into the past, the origins of our solar system, but it will provide invaluable information that could very well prove vital to future space explorers.
Whether it's mineral resources from Vesta or water from Ceres, or things I haven't even thought of yet but that Dawn will discover for us, I think it's really valuable to know what the resources are out there and what we might be able to use for very far in the future.
These bodies represent objects that could be used as outposts for future solar system exploration, as sources of materials. As well, they provide a context for our search for life within our solar system and beyond.
When that Dawn spacecraft lifts off and we're on our way to finding out about some of the biggest mysteries in the solar system, that's something we can all be part of. We can all share in the excitement of space exploration, the excitement of Dawn.
A mission into our distant past, a mission for the future, a mission into the heart of the asteroid belt, a mission called Dawn. For more information about NASA's Dawn mission, please visit us on the web at dawn.jpl.nasa.gov.